Hey guys, welcome back to another video. So in this video, I'm going to be talking about colligative properties. All colligative properties are, they're basically the properties of solutions, and we compare these properties for the solutions to the pure solvent. So an example for this is, let's say we have pure water, which is a solvent, and we compare the boiling point of pure water to, let's say, adding salt to that water, which is a solution. Now, the thing with colligative properties actually that's really interesting is the fact that the identity of the solute doesn't matter. It really does not matter. All that matters for colligative properties is the solvent, the ratio between the solute and the solvent, and sort of number of particles the solute dissociates into. So it doesn't matter if we have sodium chloride or lithium chloride, for instance, as long as these sort of constants are kept. Now, before we talk more about the four main types of colligative properties, let's talk about some basics that we need to know. So the first sort of precursor to colligative properties is molality. Molality is the ratio that I was talking about a little earlier. It's basically the moles of solute over kilograms of solvent. Now remember, molality shouldn't be confused with molarity. Molarity is something we've used before. It's probably way more common. It's this. Liters of solution. So notice the difference in the denominator. Solution includes both solute and solvent, but in molality, which we'll use a lot in colligative properties, is kilograms of solvent. The second precursor is something called the Van Hoff factor. The Van Hoff factor is essentially something denoted by I, and it's used, it's an integer number, and it's used to denote exactly how many particles the solute dissociates into when it's in the solvent. So, for example, something like sodium chloride will dissociate into sodium and chloride, so that's 2. So its Van Hoff factor will be 2. So something like calcium chloride or something will be 3 because there are 3 particles. Now, essentially all this is correlating to is how strong of an electrolyte a solute is. So if you have like a non-electrolyte, like let's say methanol, because this is a covalent compound, it doesn't dissociate into anything. So it only has a Van Hoff factor of 1. The same thing sort of happens with like acetic acid. Just because this is a weak acid, it doesn't really dissociate into its particles that much. It's gonna stay more like this than like these dissociated particles, and so its Van Hoff factor will be more or less 1 as well. Now the first colligative property that we'll be looking at is something called vapor pressure lowering. Now vapor pressure lowering is basically something related to how many sort of vapor/gas molecules can reach equilibrium. So basically how many gas molecules can escape from the surface of a liquid. Now, the reason the vapor pressure lowers in a solution is actually really sort of logical. So you have like a surface here, and you have all these, water molecules, for instance. Oops. Okay. Now, this pure solvent, water, can relatively, it relatively has a pretty okay vapor pressure. Now, let's say we add a bunch of these salt molecules to it. Right? These are the salt molecules. It's harder for these water molecules to get to the surface because of these solute particles. So because it's harder for these to get to the surface, the vapor pressure is lowered. Now, this is perfectly captured by a really important equation called Raoult's equation. Raoult's equation. You'll sort of see more of it later, and I'll definitely explain it later. But all this is saying is that and all this is saying is this is the vapor pressure of the solvent, pure solvent. This is the solution. And this is the mole fraction of the solute in the solution. And basically all it's saying is if this is 1, then if this is 1, that's basically denoting a pure solvent. And so the vapor pressure of the solvent will equal the vapor pressure of the solution. Air quotes there. But essentially, the lower the ratio of the solute to the solvent, the lower number of solute particles, the lower the vapor pressure will get because of that. The second colligative property is something called boiling point elevation. Now this actually correlates back to vapor pressure. If vapor pressure is lowered, then that means it'll take a greater amount of heat to break these attractions, and that's exactly what's happening here. Now, the boiling point elevation, or the increase in boiling point because of a solution, is dependent on 3 things. This I here is vent Hoff factor, which I talked about before. Kb is a constant associated with the solvent. So it's not the solute, but the solvent. And M is the molality. So some general trends you can get here is the more sort of particles in solution, denoted by I, you'll get a greater boiling point. This is sort of a solvent thing, and molality is sort of the lesser amount of kilograms of solvent or a greater amount of solute. You'll get a greater molality and thus a greater boiling point elevation. The next colligative property is actually something very similar to boiling point elevation, except it happens in the opposite direction. So while boiling point increases this way, freezing point lowers. So it'll take a lot less energy for this to occur. So essentially, what's happening here is actually very sort of similar trends. The greater the Van Hoff factor, the more freezing point will lower. The greater the molality, and Kf is another property of the solvent. So this is something very similar to boiling point elevation, except it's in the opposite direction. Now the last colligative property that I'll talk about is osmotic pressure. And it's actually something not really deeply covered in the AP curriculum, but I figured it's actually something pretty important to understand. Now, osmotic pressure, it looks a little different from the other equations, but all that it's saying is it's the pressure in which a solution sort of imposes when it passes through a semi-permeable membrane from one sort of solvent to another, called osmosis. Now this equation looks kind of weird, but it was actually derived from the ideal gas equation, where pressure, osmotic pressure. So for instance, if we rearrange this, it's just nRT over V, and N over V is nothing but molarity. So we get P equals mRT. Now because this is a solution, that's where we add the Van Hoff factor part. But this is sort of like a good way to wrap your head around what this equation sort of is, because it's kind of sort of intimidating to look at. All this is saying is that the osmotic pressure is directly related to the molarity, the ratio between solute and solution, temperature, and this is a gas constant, 0.0821 liters atmospheres per mole. Van Hoff factor, molarity, gas constant, and temperature. So basically, as I'm wrapping up, sort of talking about this, I'm going to do a bit of practice, but I think the reason why we call all four of these properties colligative properties is just take away this one thing, and it's that all of them have in common the fact that it's only the ratio between solute and solvent / solution that matters. We don't care about the identity of the solute in all of these properties, and that's why we call it colligative properties, because it's really the properties of the entire solution versus the solvent, not the solute. So we have a sort of practice problem here, where we have to find the molar mass of sulfur if 35.5 grams of sulfur dissolves in 100 grams of carbon disulfide, which is a solvent, to produce a solution that's boiling point increases by 3.25 degrees Celsius. So we know this is a boiling point elevation question, so let's just use that equation. Now, because we're trying to find the molar mass, what would be really helpful is to get the molality and then convert it based on the stuff that we know. So let's first find the molality. The Van Hoff factor is dependent on the solute. Sulfur doesn't dissociate into anything. So I is 1 for this equation. Kb is something we don't know, but because it's a constant, the problem will usually tell you, or there'll be like a table or something that will say. Unless it's explicitly asking you to find this, it will usually be given. So Kb in this case is, alright, Kb 2.35 degrees Celsius per mole. Okay, so let's find this. So we do that. 3.25 divided by 1 times 2.35, and we get 1.38 molal. Now all this is, if we convert it into moles and grams based on our definition, is 1.38 moles of solute or sulfur divided by 1 kilogram of solvent. Now this is also can be written as 1,000 grams because we have to keep looking at our end goal. We want to find the molecular weight. So we have to convert it into things that we know molecular weight is, which is grams per mole. So we're just using the definition to our advantage. Now we know it's 1.38 moles per 1,000 grams. And we also know right? We also know that this was in 100 grams of solvent. So we can basically do this and find the number of moles of sulfur, which is 0.138. So we know the exact number of moles of sulfur. And the reason we know this is because we use the definition of molality, which is moles of solute divided by kilograms of solvent. That's the solute, that's the solvent. This is exactly what we're doing. Now we have the moles of sulfur, and they gave us the number of grams of sulfur. So 35.5 grams divided by 0.138 gives us a molar mass of 257 grams per mole. That's our answer. Now if we want to sort of know the full answer for the formula, since we know sulfur has a molar mass of 32 grams, this is essentially about 32 times 8. So this is the molecular formula for elemental sulfur. So that's the formula for the type of sulfur used, and this is the molar mass. So this is like a good question that sort of encapsulates everything that we know about colligative properties. Using colligative properties, not just to find the boiling point elevation or freezing point depression, but to actually use it to find molar mass and other important things. I hope you guys enjoyed the video. I know it's a long one, but I hope it's helpful. See you next time.